This notebook is just a bit more example of some machine learning models. We talked about straight lines. You probably remember from school, secondary school, if you did some of the maths at secondary school level, you'll have done things like polynomials. So there's curves, y equals ax squared plus bx plus c, or ax cubed plus bx squared plus cx plus c. Maybe bringing back bad memories for people, so apologies. But polynomials are a step up from straight line curves and can be good for modeling kinks, okay? But I'm just showing them to get you more into the mindset of how we try and choose models to fit data and what they mean. Okay, so as ever, for each section, once you've uploaded this to your own Colab login portal, you just have to hit play on each of these things to go. If it doesn't work, check that you actually run all the things before and imported everything. So we're going to do two simple things. We're going to be using polynomials to fit some simple data. I'll talk about that. And then we're going to be doing some classification with a host of just different machine learning models that I'm just going to throw at you and mention some names. And maybe if you're interested in them, you might want to go and read up a bit about them, but it shouldn't then be a surprise when we're talking about them in 6 months' time. So first thing, if you didn't watch the Armin Pistoshian video that I shared previously on talking about the artificial intelligence landscape, there's a link to that here. So you just hit play and it'll play it straight from YouTube. This is part of why I like using Colab and why we use it on the course, because you can just stick in comments, text if you want to. This notebook is fairly devoid of comments and text because it's thrown together quite quickly just for coding purposes rather than explanation or teaching purposes. But you can stick in easy things like pictures or videos externally. So let's just run the first section, and all I've done here is imported or got our relevant software and tools ready. There's things that other people have made for us, so why would we bother writing the code to do them ourselves? Okay. Now we're going to do a simple regression problem. So we've got some data here, these blue points. I'll just zoom right in so that everyone can see. So simple standard regression problem. What I'll do, I'll just run it again without the line shown. I've got some data that's been made randomly here. So we've got our inputs x, and y is a function of x. And I've made this function myself, but added a little bit of randomness in there so it's more realistic. If your data looks like it fits perfectly on a straight line, there's chances are there's something wrong in there. Okay, so this is the data, and I've said, I think this data looks like a straight line. I'm going to use linear regression and fit that to the data. So I've found out what the linear regression model should be. This polyfit function inside Python does that job for me, and then I just plot that out. And all of a sudden, we've got our orange curve that looks like it fits nicely between all the data. It doesn't matter that it doesn't go through any of the data points, but on average, this is the best line for that model to minimize what we call that error that we talked about, the mean square error, i.e. the height difference between the line and each point. So you couldn't minimize the total distance from each of these points to the line by moving that line up or down or left or right or angling it any differently. Okay, so that's a straight line problem, nice and easy. What about if our data is slightly different and has a curve? You know what, I'll comment these out just so to make the point slightly easier. So this is our data. This time it doesn't follow a nice straight line. There's a bit of curve in the data. Okay, so just by looking at it and plotting our data, we can go, oh, well, that data looked like it fitted along a straight line, and a straight line does a good job. Okay. If you just try and fit a straight line to this, what does it do? Kind of looks all right, but it's missing, it's really far from this point here. The height difference between this point and the line, these aren't fitted great either. What's actually much better is when we fit with what we call a quadratic, or a y equals some ax squared plus bx plus c, a quadratic curve, if you're familiar with that. So just again, by looking at the data and thinking, what kind of a model is going to be best. That green line wasn't very good, but if you look at the height difference between the orange curve and each of the data points, it's going to be far less on average than this green line. Okay, now I've got a function here that's going to tell us what that mean square error is, or the distance, overall distance between each of the points and the curves. Now, what I'm going to do is create some random data, entirely random and structured, and we're going to fit different models to that and see which model fits the best. Okay, so this is going to churn out several different plots, and we'll go through them one by one. So to start with, I've said here's the data in the blue points, and I reckon first of all, just naively, this data is along a straight line, and it comes up with this line, and for these points the mean square error is quite low. For these points the line is really far away. So you know what, that's a bit of a rubbish model. It's got a mean square error of 12, so we're actually going to get some numbers and evaluate our models there. What about if we let that line have a bit of an angle to it? So the best line, apparently from linear regression, has a slight angle to it compared to the flat one. The mean square error is 11.96 here, so it's a bit lower of an error, but not by much. It's still very close to 12. And it's still a really rubbish fit for the point up here and for the ones down here. What about if we have a different curve? So before we found that a quadratic or an x squared curve, that did quite well. Well, it's just a bit screwed up really, for lack of a better way of putting it. It's done a curve going upwards here, so it's completely missed this curve going down here, and it's tried, but not very well, to match the curve to this data point up here. So the mean square error for this is lower though, despite it looking worse. See, on average, it's better, but for these first data points, it's worse than this line, isn't it? The mean square error here though is down to 9 from about 12. So it's a quarter better than that previous model. Let's go even more complex, and every time we go more complex in terms of our polynomial model, we end up with an extra kink in the curve, or more flexibility. And this is kind of how AI works. The more parameters or flexibility you give your model, the more wiggle room it has, the lower it can make the mean square error. So here we had a polynomial order 3, so it's a y equals something x cubed plus something x squared plus something x plus c. So it's getting better bit by bit at trying to represent the fact that our data has a curve down and then bends up. The mean square error has dropped from 9 all the way down to 3. So this is a third of the error when we've got a polynomial order 3 or an extra parameter. But it's still not quite right. As we add more and more flexibility to it, we get much lower mean square error. So here we've gone 4, and it's kind of getting this shape of going a bit up, bit down, and back up again. As you go to 5, it can go through every point exactly. This looks like it's the best model, doesn't it? Because it's got the lowest mean square error, 0.01, compared to 0.4, compared to 0.3 or 9, and it looks like it's going through each of the data points, so that's great, right? Actually, it's not the best model. It's not the best model because our data has a bit of randomness in there. Prakash, full marks for you there. This model has overfit. Well done. So what it's done is it's gone exactly through each of the data points. It's almost got far too good at doing this, and it's then not going to generalize very well. Okay. For anyone who's not familiar with the term overfitting, I was trying to think of the best way of trying to explain this, and I actually came up with a football analogy. Okay. This model has gotten perfect at running through each of these data points because it's too used to looking at this data at training. If you showed it some new data, it wouldn't fit it very well. Overfitting is a bit like me if I were a expert footballer and I played for Manchester United, if you've heard of the football team. So I play for Manchester United, and I practice taking penalty kicks every day of the week for Manchester United. I'm the penalty taker. So I practice all the time against the Manchester United goalies, and I score 100% of the time. I am the best penalty taker at Man United. I then go and play for England in the World Cup, and I go to take a penalty kick, and then against a new goalkeeper in a different stadium, I miss and miss and miss every time. See, I've gotten perfect or overfit and too good at my own set of scenarios in my own stadium, in my own comfort zone against those goalkeepers that I know and play with all the time. Put me against a new person, new scenario, new goal, all of a sudden I'm missing all the time. I've overfit to my own penalty taking scenario and not generalized very well. We want to have an AI model that's good at taking penalties at Man United, as good at that as it is at taking penalties for England. That's the one when you've got a reliable system. Ideally, you want it to be good at doing both as well, but that's a different thing. So here's the thing, we've got this data set and we've plotted it and we looked, okay, this model's a bit overfit, or as I just said, this model looks like it's doing all right. Part of our problem with this data set that's sort of screwing up some of the statistics though of this is that we've got a data point that's just way up really high over here. Now, what if this data point is an error? If we go back to the original data set where it was recorded, look at where it came from and think, oh, the sensor that recorded that information was completely off. It was running too high, or it recorded the data wrong. We're just going to delete that point. And let's see what happens when we do that. Okay, so I'm just going to say our X data is all of this apart from the last one. So all the way up until the end minus one. So it's this one, 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 this one. Ignore that one. Now let's do the same experiment again and see what happens to all of our fits. And all of a sudden things start to look a bit better. So we start off with a completely flat line, useless again. But the mean square error is 3 now, not 12. So that's interesting. This straight line's doing a bit of a better job there, 0.9 instead of 9. Our quadratic curve, or our order 2 curve, looks like it's fitting really quite well here. That's generalizing. So the mean square error is so much lower is because these models are coping much better once I've taken out this data point here. Having that in meant the models were trying to fit all of these and that one, weren't doing a very good job of fitting that one, but because they were trying to fit that one, we're doing a bad job overall anyway. So by removing that, all of the models are going to perform better. Okay. Here we've got a polynomial order 3 or a cubic, x cubed plus x squared plus x plus c. So that looks like it's fitting better and generalizing really quite well. And this fourth order model does really nicely there. Okay. It should be slightly better curved. I've just drawn, this Python code is just drawing a rough version rather than a really nice smooth version. Okay. And we're still overfitting with our polynomial order 5. It's still drawing exactly through all the points. So this fourth order model is the most appropriate here, it seems, for the data set with and without that high point. But our other models don't look bad at all. The real question is, are we actually okay in taking away that data point? Just because it's what we call an outlier, is it truly bad data that needs removing, or are we just making our model to look better by taking it out? Okay, and going back to my children's hospital problem that I talked about and showed you the data set from, if I had a patient that when I did my analysis of how accurate my model and my algorithms were, and I was getting loads of false alarms on that patient, would it be right for me to delete their data and just say, well, there must be something wrong with the sensors there, I'll just get rid of that, and all of a sudden my false alarm statistics look really good? Is that correct or not? I need to go back to the clinical experts and say, look, I've got this data, it's making my algorithm look really bad, but if we take it out, it looks really good. What's wrong with this patient or this data? Is it my algorithm or is it them and the data? So you need external validation more likely than not to try and prove that. Okay, so that's an example with fitting some data with polynomials, and if you were interested, you can apply some of these tools and techniques and try and use them in the hack on the data. Okay, and I'll talk about that later on. So what about classification? So we've had regression where we've got some data and we've tried to draw the line or the curve that goes to that data, and the idea is then now we can predict ahead in the future or see what's done in a different way. Well, thank you, Atif. So classification is about taking some data and then putting it into discrete sets. We're going to look at a nice real data set I'm just going to set up some display mechanisms there to make sure they're all working. Okay, and we're going to bring in a data set. I'll just run this because it's going to show the data set. Ignore the plot on the top first of all. So this data set is called the SA Heart, or South Africa Heart data set. So it's a set of information about some people, some employees of a factory in South Africa. And there are 461 different rows in this data set. You can get rid of the not a number ones and filter the data and clean the data. There's not a lot of cleaning required. It's been formatted and prepared for people to test machine learning algorithms on. Okay, so it's not an overly complex data set, but it isn't an easy one to do very well in, and we'll see that in a second. So for each of these people, we've got a whole set of different features or variables or bits of information stored about them in the different columns of our data table. And what we're interested in is whether or not these people have coronary heart disease, or CHD, as we're going to call it. So do they have a problem with their heart that's going to then need medicating? Now, from an employer point of view, naturally you want to be supporting your workforce ideally and making sure that you give them time for medical appointments, but also not putting them in stressful situations or situations that would be bad for their hearts. So maybe you need to move the workforce around based upon those that do and don't have coronary heart disease. But testing for that requires a medical appointment, requires sometimes work with a cardiologist and assessments and things that can either be expensive depending on the country you're in and the healthcare system, or can just be problematic for the people to get the time off to do, or stigmatizing. So what if we could just get some information about people and then predict whether or not we think they have coronary heart disease? That way we don't need to put burden on the medical system, we don't need them to pay, we don't need to have all the stigma and stuff. We can collect some of this information without them. So here's the thing. Let's look at the information. So whether or not they smoke, like what their tobacco levels are in their blood, what the adiposity is, whether or not they've got some measurement from this type A test, what's their obesity level, and these are all quantified from medical point of view. The thing is, for this point of view of today, we don't care too much about those things. If we wanted to come up with a realistic screening system, obviously we would work with medical professionals based on all the things I've talked about today. What's their age? Do they or do they not have coronary heart disease? Do they have a family history of it? So do they have a family history of it? Yes. Family history? No. Okay, that could be summarized in a single thing, but for this data set, it's separated out. This is the column that we're interested in though. Do they or do they not have coronary heart disease? So what we're going to do is remove that from our data table and then use all of the remaining information to try and predict for each person, do they have coronary heart disease? Just to show how difficult this is going to be, here is one of the variables, type A. So plotted, so their level of type A score and whether or not they have coronary heart disease, 1 being yes, 0 being no. And you'll notice an almost direct overlap between type A score for most of these people, where each circle represents a person. There's almost a perfect overlap between their type A score and whether or not they have coronary heart disease, i.e. type A in and of itself is not going to help us predict whether or not they have coronary heart disease. What we'd want, if it were going to be a useful score in and of itself, is type A down here for 0, up here for 1. And then we could just draw a nice line between the two and go, okay, if type A is greater than a certain value, then they've got coronary heart disease, or lower than that value, they don't. But we can't draw a nice straight line and go yes, no here. Okay. So what we're going to do first of all is try and just use a polynomial model for that. I've dropped the last bit to clean that data and get rid of that for us, and then showed the data again for you. We're going to use 70% of the data to train and 30% to test. Okay, I'm not randomizing the training test sets, we're just going to use it as standard. Okay, but then we can test to see if our models are reliable or if they're overfitting. And if they're overfitting, then you're going to see very different scores for training results versus test results. Okay, I'll reiterate that in a second. So we've split up the data set and we have 323 people in our training set and 138 in our test set. So we can use a polynomial model that we've just talked about. We can try and do that and see if it works. The thing is, to get a polynomial to do classification, you need to mess around with it. Okay, and this all looks a bit scary if you're not familiar with the coding stuff. Don't worry about that. What I'm going to highlight to you is this bit here. To make our polynomial model, or our model that was good for fitting regressional data and curves and things, work to be able to classify, say, yes, they have coronary heart disease, or no, they don't, we have to, a bit like that data wrangling, and bash it into our framework. We're bashing a square peg into a round hole here. A polynomial in and of itself is not supposed to do this job, and to make it do this job, I've said, we're going to take the absolute value and we're going to round it. Okay, so I've had to mess around with it to make sure that it does classification. It's not designed to do that, and I'll show you why, because if I take this out all of a sudden and we get rid of the fact that it's rounding and taking the absolute value of it, making it always positive, and messing around with that, as soon as I take that out, it's broken. The code doesn't work. It doesn't like that at all. Okay, so you can get it to try and do stuff for you like classification, but it's not supposed to. So what we actually need to do is use classification algorithms for classification, models designed specifically for that job. So we're going to start with logistic regression. Okay, so this is the model that I introduced. We're going to, again, make sure we've got our train and test data all split out properly. And remember when we ran the logistic regression algorithm yesterday, we got different results depending on who was running it, what time. If you ran it over and over, Abdullah, I think I set you the challenge of seeing if you could get the model down to 0% because you said it was getting worse and worse each time you used it. So what we're going to do is run our model, and I'm going to run a logistic regression, a standard model, using a training framework, a specific training framework, and to see how generalized it is or what the difference is in that, I'm just going to run it 3 times and see if the results are the same for each of those 3 runs. And they're not, actually. So the first run, it trained on the data set and got 66% training accuracy. So 66% of the time, it could predict, based on the data, whether or not someone had coronary heart disease or not. I mean, that's only 2/3. That's not great at all. If it's 50-50, then you might as well flip a coin. Or 50%, then throw away your AI algorithms and just flip a coin, because it's not worth the computational overhead. It's not reliable. 2/3 of the time it's accurate, so there's 1/3 of the time that's not accurate. Still not great. So 66% of the time accurate on the training data, 68% of the time accurate on the test data. So that doesn't look like it's overfit there. It's about the same, give or take a few percent. That's absolutely fine. The second training attempt, it did slightly worse on the training, better on the test, or the same on the test, sorry. The third time we trained it, it did rubbish on the training data and even worse on the test data. So it had overfit, but it just done a bad job on both. I mean, like I said, that's less than 50-50, so there's no point in having an AI or machine learning solution to this problem if you're less than 50-50. Okay, logistic regression with that training approach wasn't any good. The best way to use logistic regression generally is to use this particular training methodology on simple data sets. So let's try the best way and see. We've gone from our rudimentary training approach using stochastic gradient descent there. It's called, if you're familiar with those terms, great. If you're not, doesn't matter. You'll learn about them on the course. But using this approach, it's always going to come up with pretty much the same results. And this time it's done much better. Almost 73% training accuracy, 75% test accuracy. So it's not overfit on the training data because they're within a few percent of each other, and it's done slightly better on the test. So great. It's generalizing quite well, and it's right about 3/4 of the time. Okay. Logistic regression is one approach. It's still a bit of a black box. And remember, I talked about this yesterday and the day before. You've got this black box, this AI is doing stuff, and people don't know what it's doing. We can, with logistic regression, try and explain some of what it's doing and look at how important it thinks each of the individual features are. So it'll rank them differently based upon what they are. But instead of wasting time looking at that, I want to move on and just throw a completely different approach to you. So just sort of my spelling error there. That's going to annoy me. So what about decision trees? So decision trees, look at a whole data set and then try and make a load of different decisions And based on all of these decisions at each layer in a hierarchical approach, it's going to decide then whether or not someone has coronary heart disease, yes or no. Okay. The lovely thing about decision trees is that we can run them very quickly. We can see what they think of each different feature, and then we can plot them out and see what's going on. But first of all, we should look at the results. So I've run decision tree twice on this, training them and to see what's going on. So Prakash, yes, logistic regression does use gradient descent or a gradient descent style approach. It's the first time I ran it, I used stochastic gradient descent, so SGD, in a particular way, which is good for big data. But the second time I used it using the BFGS solver, if you're familiar with gradient descent style approaches. So that's a far more reliable but slower approach. But it is gradient based. It's more of a Newton method than a gradient descent. Okay. Again, if you're familiar with it, great. If you're not, don't worry about it whatsoever. So decision tree has trained, and I've trained a decision tree first of all on the data, and it says on that training data I am 100% accurate. On the test data I am 60% accurate. That is we've dropped 40% accuracy using this decision tree straight away. So you know what, it's overfitting. The nice thing about decision trees is you can almost claw it back a bit and say, look, you're going to overfit, and they tend to overfit. So we're going to pull you back, rein you in a bit and say, look, don't overfit, try not to overfit, let's put some constraints in. So I've rerun the decision tree by restricting it and saying, here's some limitations on what you can do. So use a maximum level of 4 trees or branches in that tree, and then we'll see what's going on. So Edna, why do we train and test? If I just run it on the training data, then this model would say it's 100% accurate. And then if I went out to use it in the real world, it would only be 60% accurate. We can evaluate that. Okay, to say here's the reliability score of the data. Okay, by doing train and test just with the data rather than before we go out to the public and test it in real world, we can get a measure of the reliability of that model, and we can see that it's not reliable, or our training accuracy isn't reliable in the real world. So we've gone from 100% down to 60%. If someone had said that our vaccine is 100% accurate, and then we went out and actually in the public it was only 60% accurate, that wouldn't be very good. It's almost like a control group. So what they do when they're testing the accuracy of the vaccine, they'll have gone and said, our training accuracy is maybe 73%, but our test accuracy is about the same, therefore it's reliable. So I'm going to leave that up to you, actually. If you're interested, go away, take the notebook, and all you need to do if you want to change that around is it changes 0.7 to a 0.8 and see what the impact of that is. And you could rerun all the experiments and see if your results are much different. Okay, great. And anyone else, if you want to change that, your models will generally, they'll be about the same or they'll overfit more, I would expect. But it's an easy experiment for you to run and gives you a bit more hands-on experience with that. So I've restricted range in this tree and we've pulled it in and gone, right, more constraints, less flexibility, try not to overfit. And it's gone from being 100% accurate train, 60% test. It's gone 73 or 74 or almost % train, 74% test, pretty much. I'm happier with that. That's generalizing much better. And really the test accuracy is the more important thing for us here. That's the thing the public would care about. We can see the features that it thinks are the most important as well with a decision tree, nice and easily. So it thinks that age is a really important factor. Then their type A score, so this is a worthwhile test to do if it's a medical test, it's quite informative. Then things like obesity, alcohol usage, and whether or not they spoke, as well as IDI. So we've got a whole host of different features here, but we can see the importance of each of the different ones. And that gives you, as a layperson or person who hasn't trained the model, gives you some confidence in what the model is doing. Okay. When you take this to medical experts and say, AI algorithms trained and these are the things that they think are most important, they might go, Oh, that's interesting. We always thought age might be, but we never thought the type A was that important. But now that we know that, I can see why it is kind of, yeah, okay, we'll put more effort into doing type A tests. So let's have a look at this decision tree. And we could do that with decision trees far more than, more so than we could do that with other algorithms. So let's see what the decisions are that it's making. So for every person, it asks some questions of those people and then goes left or right, left or right, left or right. So if it moves down to the left, it's true, down to the right, it's false. So is the age less than or equal to 30 and a half? If the age is less than 30.5, it moves down to this decision block. If it's greater than 30.5, it moves into this block. So here we've got a next decision point. So if their age is less than 30.5 and their tobacco usage is less than 1.055, move to this block. But if age is less than 30.5 and tobacco usage is greater than 1.055, we're down here. Next decision point, so we're gone. Age is less than 30 and a half, tobacco is greater than 1.055, but alcohol is 11.105. Then we think that out of the data set, the training data set, there were 8 people there. We think that those 8 people all have coronary heart disease. But if they're less than 30 and a half, have a higher tobacco than 1.055, have more alcohol than 11.1055, and have a type A score greater than 53, then we think they have no coronary heart disease. So this thing, you can follow down each of the decision points one by one and see which way it's sorting the data bit by bit, and it's making hard decisions that we can interpret, understand. And if you take this again to a medical expert and go, these are the decisions it's making, then they might look at areas of the tree and go, I can see why it's making that decision, that decision. That one doesn't make sense to me. But when you look at the next decision, it kind of does. So it's giving trust back in the machines. Okay. So the thing with decision trees are they're nice and quick and they make decisions, but they're slightly random the way they set up those decisions. So sometimes we use something called a random forest. So instead of just having one tree, why not just train loads of them and then add them all together or group them together somehow using what we'll call an ensemble, borrowed from orchestras, and then see how that performs. So sometimes a random forest can be much better than a decision tree because it's taking loads of different models and averaging them. It's not always guaranteed though. So here our random forest has overtrained, and it is more likely to overtrain than a decision tree on average. So your random forest here, the accuracy for training is 97%, but the test accuracy is 71%. So that is worse than our constrained decision tree for test. Okay, test is the thing that we're really looking for, as well as assessing whether or not they've overfit. But random forest is using more of the features more evenly rather than a decision tree, which just focused in on a few features. So this decision tree in and of itself for this problem is using less information and being more accurate. So that's more efficient and better on average. But that's only for this data set. Another approach is to use something called k-nearest neighbors. Okay, so k-nearest neighbors is saying, okay, I'm going to take some of my data and then I'm going to look at a new person, say Tom, and I'm going to look at whether or not Tom, the data for him, is similar to Janine. So you've got Tom and you've got Janine. If Tom's data is really similar to Janine's data, then chances are Tom, whether or not he has coronary heart disease, will be the same information as whether or not Janine has coronary heart disease. Now, if you do this over and over with lots of different people, so you compare Tom not just to Janine, but also to Dave, to Jaswinder, to Toluropi, you're going to all of a sudden get a much more reliable measure by seeing who Tom is closest to. And you don't just have to take his closest person, you don't just have to say, he's still closest to Janine, or he's halfway between Janine, his data, halfway between Janine and Toluropi. Well, actually, he's going to behave a bit like both of them. Or we're going to average out, we're going to say he's close to Janine, Toluropi, and Dave, and Jaswinder. So we're going to use 4 of his neighbours, 4 closest people that his data is closest to, and from that we're going to average and say we're going to expect you to have the same outcome of coronary heart disease as they all have. That's called k-nearest neighbors. Now you can use one neighbor, so you can just use Tom and Janine, or Tom, Janine, Dave, Tom, Janine, Dave, Jaswinder, Tom, Janine, Dave, Jaswinder, Tolu, and Opie. You can use multiple. We're running an experiment here with different numbers. So number of neighbors being n. I'm going to start with 1 and see how accurate we are. I'm going to then have 2, 3, 4, 5, 6, all the way up to 15. We're just going to run our experiment over and over, and it's really quick, nice and easy to do, and we'll see what the error is. So which model performs best? And it's not necessarily going to be the one with the most neighbors. Often it's something with a relatively small number, but not 1. So if we start with n equals 1, our test train accuracy is 100%. It looks great. Our test accuracy is rubbish, 63%. We need to up our game there. So let's use 2 neighbors, 78% train, 68% test. We're overfitting still. So you tell you what, let's drop it down. Let's use 3 neighbors. So we're going to compare Tom to Janine, Dave, and Jaswinder there. So all of a sudden, 76%, 73%. It's all 72%. So we're not overtraining very much. We're getting more realistic. 5 neighbors is getting better for overtraining and getting quite a good test accuracy. So there we go. 5 neighbors seems to be quite the good fit. It's the best situation, really. So you can do that. You can use different ways of comparing whether who Tom's neighbors are and who he should be closest to, and weighting those differently. But on average, it seems 5 is the best. If you've done any sort of machine learning before or watched any YouTube videos and stuff, you've probably heard the term support vector machine as well. It's a bit more complex, and I don't want to go into any of the details of the complexities of it today. It's what people would consider a standard good machine learning classifier, and it's quite flexible and complex, but it is computationally quite expensive if you've got big data. But support vector machines, let's just run a quick comparison with them. There are loads of different setups for them, different parameterizations, different choices of the way you can set it up to train it, work with it. So you know what, I'm just going to use 4 different setups that are fairly standard, borrowed from what people who are experts with support vector machines use, rather than me go along and say, I know best, I'm going to do it like X, Y, and Z. No, use what experts say and see, but every expert has their own way of doing it. So borrow a few experts, their setups, try it, adapt it, and see. So whether you use this first setup, it overtrains massively. Second setup, it's not doing a great job. Third setup with a polynomial kernel or polynomial as part of the setup of that support vector machine, it does quite well. But actually a linear kernel or a straight line part of that does really well. That's the best support vector machine. So, and it also doesn't overtrain very much. So remember what I said about random forest, where we said, you've got one decision tree, it's good. Why not just have loads? Ensemble, join them all together, see what they all say together. We call that a mixture of experts or ensemble learning. But we've been kind of coming up with lots of different models as we've been doing this notebook. We've done logistic regression, we did that polynomial thing at the start, we did all sorts of different logistic regressors, k-nearest neighbors, polynomial, support vector machine, we've done decision trees, we did a random forest too. Why don't we just ensemble those and see, maybe they're getting about, let's say they're getting about 70+% accuracy individually. What if we're getting 70% accuracy on different parts of the test set? And actually, if we join them together, maybe we'll get a better classifier overall. And often that's the case. Today's not our lucky day, though. So if you join or ensemble the models together in a simple ensemble, I could spend a lot more time doing this, but I'm not going to today. So our training accuracy jumps up to 97.5%. Our test accuracy is about 71%. So it's still similar to what the other models are getting, but not quite as good. So actually, we're better off just using an individual best model rather than joining together best and okay models. So let's just look at all the results, print them all out, and see which one did the best and plot them so that we could get a comparison. The actual best model here is logistic regression. So we try these more complex, more variable models. I'll do a 5-minute break in a minute, in different ways, and we plot them. Actually, the best one was logistic regression rather than anything more complex or flexible. And it kind of goes into that situation of it looks like the AI is doing bad, some of these more complex AI models, but actually some data sets just favor things like logistic regression, and others favor these other models and tools and techniques. With data science and with AI, we have to try different things. We can't just have our favorite model and always do it the same. You can't always say, I'm always going to use deep learning, and deep learning is the best because that's what Google do, or Microsoft or Amazon. They know what they're doing. No, try different things, evaluate, be robust, see if it suits the application domain, and go from there. And you know what? Maybe for coronary heart disease, 75% accuracy is good enough. If you're interested, you can extend this and go on even further and do a different classification problem. So the code's left are completely empty, but there's some great examples online. Give it a try if you're interested, and do handwriting recognition or handwritten digits. So these are the numbers 0, 1, 2, 3, 4. Okay, there's a data set in here where I've split it into train test, and you can try and predict whether or not the handwritten digits in this data set are, say, 0s or 1s or 2s or 3s or 4s. And you might think, well, why do we care? Why do we need machines to read handwriting? I can do that. I'm sure you can, but you can't do it as quickly as the US Post Office needs you to do, or the Royal Mail Post Office in the UK, or any national post office. See, so many letters get sent through the postal systems or packages that need delivering, that they need automated systems to look and read the handwritten addresses that people have written on letters, to then funnel them into different areas and sort them out so that they can work out, if you're sending a letter from Cornwall in the UK, so bottom left corner of the UK, and it needs to go up to Edinburgh, that needs to go on a plane. It needs to be flown up there and sent. Whereas if it's just going to Devon, the next county or town over, you need to put that in a different pile, because then that just needs to go in a van and be delivered that way. So you need a handwritten recognition system to be able to look at those letters, filter them and funnel them on different conveyor belts so that it can be efficiently sorted and sent. And that's this problem. Can you get an AI system like logistic regression or any of these other algorithms to do handwritten recognition? Nice simple problem, not overly easy to get 100% accuracy on, but generally deep learning will get you 99% accurate, if not more. Okay, we're going to stop there for a quick 5-minute break, everyone, just before I move on to the next part. But has anyone got any questions before I stop? So here's the result for the random forest. It's 0.71 test, and here's the result for decision tree, 0.739. So that single decision tree I trained did better than random forest, but if you used a different random seed, then the decision tree might be worse than random forest. Prakash, it's there's an element of randomness to how they start themselves off and choose and the way they work. Interestingly, for anyone who's come across it, so Xbox, if you've seen Xbox, the Kinect thing, the camera that sits in it and takes a photo, it does video recognition of you, but watches you moving around, hand signals and stuff, and you can play games interactively with that. Have people come across the Xbox Kinect? It was the most widely sold piece of tech in the world at the time. The researcher who headed up the Xbox Kinect system, the AI behind that, was a lecturer at Aston University in the maths department where I trained. He went to work for Microsoft Research, so he and his team created the recognition algorithm that understands people's hand movements, gestures, movements, identifies their body parts, their hands, their feet, that then lets you interact with the game. That uses decision trees. So this decision tree that we've done here is the same algorithm that they've used on the Xbox there. They've had a bit more control over it, but that's what it's doing. Okay, so we'll take a 5-minute break there, and I'll get myself set up to do the next notebook, which is going to be the introduction to the hack thing. It's going to be the same notebook actually as our first one that we did, because that's got a bit about the data set and showing you how to do some of that part. And you'll see, hopefully, okay, you'll see from what I'm about to show you that I'm not expecting an awful lot of variation in the code, but also you're working as a team of 10 and will be supported by Yasmin and Mohammed as well. Okay, so 5-minute break and we'll be back soon. Okay, everyone. So hopefully I've not scared everyone off by just throwing a load of different machine learning models, tools, techniques, and things at you all. As ever, if you've got any questions about them, interested in any of those particular things at all, feel free to go back over the recording, look at the notebook, run it all again yourself. And if you're interested, I think it'll be probably good to spend just a little bit of time looking at that decision tree and seeing some of those decisions it's making and trying to understand from a human point of view, if you think that's motivated properly, or if you can understand why it might be making some of those choices and decisions. Also, like Shamaya had suggested, change that 0.7 to a 0.8 or down to a 0.6. See what happens if you vary the train test portion of the data. Okay, and that's what I love about machine learning and these coding notebooks and things. It's just very easy and simple to change little bits to see what the impact is. And as Atif suggested, you can then make those small changes, see the impact, and that's how you start to understand what the code is doing and the whole system as a whole. Okay. So just to double check, does anyone have any questions before we move on? Okay. So can I just check, can people still see this, can they see this notebook on the screen? Perfect, thanks. So this is our first notebook that we actually did with the whole hello world, the adding up and all that stuff. And you know what, I'm just going to skip right down to this section here called data manipulation with pandas. I'm going to click on here and do runtime and run everything before. The main reason I'm doing that is because at various points above this, we've imported the different libraries, datasets, tools, and techniques and code that other people have created. You're going to hit an error because you won't have uploaded the Hubble data. We don't need to do the Hubble data though. We did that on Monday. We don't need to do it again. That we didn't load in anything that we need in that at the moment. What we actually need is to move to this part though, data manipulation with pandas. Okay, I'll just zoom right in. Now, I'm going to introduce the data set first that you're going to be doing for the working on for the next couple of days as a group, and then I'll explain what I want you to do, or what I want you to submit at least. Okay. So I'm going to load in this data. Now, I had to upload this data, and to upload a file, just a reminder, you click on this folder thing here, the up arrow there, to upload, and then you can upload citytemperatures.csv. That's in the folder that I've shared with everyone. Okay. If anyone could just reshare that file, the files link to the Google Drive, that would be helpful. Thanks. Just so it's at the bottom of the chat. So this city temperatures thing is 130. Thanks, Alice. It's 134 meg, right? So it takes a little bit of time for you to download. It takes a lot longer for you to upload into the cloud, because with internet speeds, download is about 10 times as quick normally as upload speed. So what we did have happening is, as it was loading in, it appeared here, looked like it had loaded in, but what there was, and I've just been a bit quick, if you want to go back in the recording and see, it said the name of the file here with an orange loading bar, and bit by bit went round. So the thing is, you could start to try and work with the data before it's even fully loaded, and this is the cool thing about CSV files and with Python and things. You don't need to have the data set fully loaded in to start your analysis. But so you can start it, but actually what we want is the whole data set loaded and ready to make sure we don't miss anything. Okay. Now this is a data set of temperatures of different cities. Okay, and I think what I might just do is just take a break from Python for a second, and for illustrative purposes, we're going to see, unfortunately, my messy folder situation there. So I'll just hide that. I'm going to show you what this data set looks like in Microsoft Excel, because that would be the standard way you try and open if you double click on the file. So I've double clicked on this. It's going to take a minute because it's a big file. It's going to think about it. The data set is too large for the Excel grid. If you save this workbook, you'll lose data that wasn't uploaded. So I don't know if anyone has ever worked with a data set that is too big for Excel before, that has more than 1 million records. So we're working with some fairly, what seems like chunky data. Actually, this pales in comparison to really big data, but it's really great experience for us to work with. And this is why it's nice to work with Colab in the cloud, because it doesn't matter about what your spec of your computer is. Okay, we can get away with using cloud resources and not slowing down yours. But this data set, just to get, one of the first things you should always do with data is have a look at it, get your eyes on it to understand some of the different features or variables, what's being recorded and what's going on. So it's got regions, countries, and this broken down then into cities. So a city of Algiers, for instance, if we jump on down, you've got Sapporo there, where in Japan, you've got Vientiane in Asia, Singapore, for instance, and we only just moved out of Asia as we hit 597,000 row. Okay, it's then got what the month is, so that'll be 1 being January, 2 being February, etc., all the way up to December 12, and what day of the month as well, what the year is, and then the average temperature recorded in Fahrenheit. Okay, we'll deal with that in a second, because I don't like Fahrenheit. I can't. It's really hard to compute it if you're not used to it. So I prefer to convert everything to Celsius. Nice and easy to do in Python. You couldn't just do it in this, it would take ages in Excel. But this is the bit we're interested in, the city and the average temperature on that day in that city. So that's what the data looks like. And the fact that you can't just open it all in one go is quite interesting, at least from a teaching point of view for us. So let's just load it in, and in 1, 2, right, it's loaded, or the whole data set in one go in just over 2 seconds. Nice and quick. Let's have a look at the first few rows of it in Python. So it looks about like it looked previously. When it's imported, Algeria doesn't have states as per this data set. The states are primarily for a couple of Chinese provinces and for the USA. So most of the others will just have not a number, which is what NAN stands for. It just means when it's tried to import it, it doesn't know what to put in there, so it's just put in an error code for itself. Then it's got the city, the month, the day, the year, and what the temperature was. Okay, I'm going to do a description of this, data.describe, just to get Python to tell me what's going on really. But it's not overly useful. So how many of each of these different features were recorded, or how many rows are there with data for each of these? So we've got 2.9 times 10 to the power of 6. So 2.9 million rows. So about 3 million data points there for us to look at. What's the average temperature for the whole world from 1995 all the way up until 2019? 56 Fahrenheit is the average temperature, apparently. It's not an overly useful statistic, right? But if you've got a smaller data set, describing it can be useful. Now, let's have a look at how many of those values are what we'll call not a number. So, Ulka, hash is just a comment. This is a comment and won't do anything. So it runs exactly the same whether you've got it there or not. But we leave comments in our code so that we know what that bit of code is doing. Because even as computer programmers who've got years and years experience writing and developing code, you still can't read it and know exactly what it's all doing all the time. So when you've got a few lines of code doing something, we stick a comment in to remind us what we're doing. Otherwise, if I just looked at this code and went, why have I done that? If I did it not just even a year ago or 10 years ago, if I did it last week, I'd struggle to remember, why have I looked at the unique regions in this data set? What is this data? What's going on? So leave a comment there and you go, let's see what the regions are in the data frame. Well, that makes sense. So Edna, what's the difference between is null and is NA? So is null is going to be empty ones. Is NA all null values? Is NA is not a number. Okay, slight difference, but for most of us, it doesn't matter. Okay, but most of these actually, it just seems that states are the ones with not numbers. Okay. I'm just going to rerun each section of code as we go. So what are the unique regions in our data set? That's going to be useful for you choosing your focus later. So we've got Africa, Asia, Australia, South Pacific, Europe, Middle East, North America, South Central America, and Caribbean. Pretty much the whole world then, should we say. So, as I mentioned, the temperatures are stored in Fahrenheit. I don't want to work in Fahrenheit, I want to work in Celsius because it's much easier for me. Okay, so they're stored in Fahrenheit and we want to convert. So all we need to do is have a function that takes every single row of our data set and one by one looks at that row and goes, take Fahrenheit, convert to Celsius, convert to Celsius, convert to Celsius, convert to Celsius, and it'll do it very quickly. Like I said, you couldn't do it to all of the data in Excel because you can't even load all the data in Excel. So the function to take something from Fahrenheit to Celsius is to take the value, and we're just going to call the value rho. So Fahrenheit value being rho minus 32 times 5/9. And I'm just going to round that to 1 decimal place, just to be nice and easy. Okay, you could have it to more exact things, but there's no point. We only care up to 1 decimal place today. So this is a function that's created. That's like a conveyor belt that's set up. If you're not familiar with functions in maths or programming, this is a conveyor belt I've created that takes Fahrenheit data in and puts out Celsius data. I just need to get my data and throw it one by one onto that conveyor belt. So here's my conveyor belt function called toCelsius. That's the function name. So data, the average temperature column, I'm going to overwrite that. So I'm going to say the elements of the average temperature column are going to be the current elements of the average temperature column, but we're going to apply the function toCelsius. toCelsius, this function here. Okay, don't worry if you don't understand it, just look at it a couple of times, it'll sink in a bit what it's trying to do. So if I run that, it's going to one by one go through every row, run it all, and now if we print it out again, our average temperatures that were in Fahrenheit before are now in Celsius. That's great. Bob's your uncle. Job's done, yeah? So we're in Celsius. Now let's start to do a bit of exploring in there and get a human understanding of what's really happening in this data. So we might need to do a bit of wrangling, a bit of cleaning, a bit of processing, and then we could try and get some knowledge and information out. So I'm going to do this as an example with a single city to show you how to do that, and then you can take the code, just change that city or change the process or look at what it's doing and then, you know, muck around with it a little bit and try and get some understanding in your own groups. Okay, so I'm going to group by region, then country, state, and then city, and look at the year, the average temperature for each of those groups. So what this means is it's grouping North America, so all of the US, by each state, it's grouping it. So for the year 1995, the average temperature is 27 degrees, apparently. For 1996, it dropped to minus 15. 1997, it looked like it was 15. So it looks like some weird stuff's going on in there with Puerto Rico. Okay, let's get a bit of a closer look. Instead of focusing on things like Puerto Rico, I'm going to jump straight into Vienna. It's a great city. If anyone's not been, highly recommend it. Now, I'll just jump to this question here, Edna. The row in the function stands for what? So the row is just in a function, when you set up this conveyor belt, whatever you put inside the brackets of the line that says def, so what the function is called, and it's called toCelsius, and then row. Now, row is the item or the box that sits on the conveyor belt. So the stuff that's happening to row is the stuff that's happening to the box row that then gets messed about with on that conveyor belt as it goes along and then gets chucked out, and whatever is after this return is what's actually put out at the end of the conveyor belt. So we've got a function called 2 Celsius. We put the box on that's called rho. We mess around with the box to convert Fahrenheit to Celsius, and then we return the Celsius value, which is just the output of this function. Yeah, that's great. Thanks, Ashraf. So Vienna, let's have a look at Vienna. We're going to just get the data first of all, and just rather than working with the whole big data set each time, we're just going to create a new variable, we'll call it, called Vienna, that's got the data for Vienna. And then no more working with data, no more messing around with all of that stuff in there. We're just working with Vienna now. So Vienna is copy the data out where the city is called Vienna. Change this, and then you're ending up working with a different city altogether. Now Vienna is, we're going to group the data for Vienna by year first of all, and then look at the average temperatures, the mean. And I'm just going to get rid of the columns month and day as well, and then print out what's going on. So for each year, 1995 to 1999, what's the average temperature? Apart from Puerto Rico, actually, that was looked a bit of a mess. Actually, this makes sense. So 10 degrees, 8 degrees, 9 and a bit degrees, almost 10 degrees, 10 degrees. So average temperature looks relatively standard along those, stable. Okay, that's all well. So let's have a plot and see what's gone on then. So that was only the first few lines. Remember, head only shows you the top lines, okay, top 5. Let's have a look at when we plot the average temperatures and then plot a line of best fit through them. And wow, what happened in 2020? Do we think that in 2020 Vienna suddenly had a massive cold snap and dropped the average temperature from about 10 degrees all the way down to 7 degrees? Wow, that was very quick. Missing data, great. Let's have a look and see if we've got some missing data going on here. So now if we just look at the end of the Vienna data table, rather than the head that we looked at here, the head, we're going to go down here and look at the tail, the bottom. So the bottom, 2016, 17, 18, 19, 2020, average temperature, 10 and a bit, 10 and a bit, 11 and a bit, 11 and a bit, 11 and a bit, down to 7. Let's have a think about this. What was the average data for the month going to be? So if you add up all the months 1 to 12 and take the average is going to be 6.5, because it's halfway between 1 and 12, right? So all of a sudden we've got 6.5, 6.5, 6.5 for all of those. Average month is only 2.7, so we've only got data in 2020 up until halfway through the year. Missing data, and it's not got the whole of summer in there to bring up the average temperature. It's got some of the cold data at the beginning of the year, not got the warm data, not got the cold data on the other side. So it's 2020, we have to discount then if we're going to do any real robust analysis and go only up until the end of 2019. Okay, that's important to remember. Otherwise, it could be a big constraint on your model. So I'm going to take the data for 2020 and then plot that and look at it compared to 2019 and 2018 and just see how much of the trended data is missing. Okay, so I'll rerun this, but I've kind of ruined the story there slightly. Zoom back in, and then let's get right in close and look at this plot. So we've got 2020 in blue that we've plotted. So it does this for each year grouping year. So I'm just going to put a comment in here. Get 2020 data and plot. Copy the comment. Get 2019 data and plot. Get 2018 data and plot. So we've got data for 2018, 2019, and 2020. And we can see, yeah, we've got the start of the curve, so like that up to about there, but we're missing all this nice warm summer weather. So no wonder the average temperature is a bit low. Now, what's gone on with 2018 and 2019 then? Any suggestions? We've got a lot of, down and up weather, down and up, down and up. And then all of a sudden, some days were about minus 70 degrees. So perfect, Prakesh. Seasonality, summer and winter effects, annual effects, great, love it. What I was really trying to jump at is, do we really believe that it was minus 70 degrees on some days in Vienna? No. Outliers, yep, and it happens that they're actually bad values. So we can break it down. They could be bad values from plot. It could be plotting them like this for one of three reasons. They could be null values or empties, not a numbers, or really low numbers out of nowhere. So if I run this again, they're not null values. They're not a number values. We're focusing just on 2018 here because that's what sliced is the data for Vienna for 2018. So there are 3 times where the value was less than minus 20. Okay, and I've just used that cutoff because I can see by eye it's less than minus 20. There's a problem there. Okay, so let's look at what those values actually were. So these are the rows in the data set where it happened. Bad data entry, yes. Let's have a look. So let's have a look at the variable slice that we've got. So that's the Vienna data for 2018. And we can see that it's for Austria, Vienna, one day in January, on the 4th of January, and the 14th and 15th of November. We've got minus 72.8. It's the same temperature down to 1 decimal point. Well, that's quite unlikely, isn't it? So we've got some bad data, and we need to clean that out. We can do that in 2 different ways. We can either just yank it out of the data set, or we can fill it in. And I'm going to show you one way of yanking it out and 2 ways of filling it in. So we're going to yank out the first one, just go, right, this is the row number 641048. That's on the 4th of January. That's a bad value. I'm just going to drop it. So just take it from the table and drop it out, and it's gone. Job done. So what about the other 2? If you've got lots of bad data, but you need to do something still with the data set, then you probably want to go and fill some of that in. And that's what we call imputing, a bit like I did with that medical data. Now, you can do it a host of different ways. What I'm going to do is show you, so we've got missing data on 2 days next to each other, the 14th and the 15th of November, right? Rows 641362, 641363. So I'm going to look at what happened to temperatures either side of those to get an idea of, if it was some sort of trend, some sort of curve, or a straight line increase that was going on, and it's just these 2 are missing from the middle. So here's the data for each of the days around that, so from the 12th to the 17th of November, and these are the 2 that are missing. Now we can fit it in a couple of different ways. If you've done any statistics before and are comfortable with that, then you can fit it in using the mean value of data either side. So 641362, this one here, is missing. I'm going to say that the value there is the mean or the average of the value just above and the next good data point afterwards. So it's going to average 9.3 and 2.8. So all right, get that row 641, get that row 64364, and I'm going to add them together and times them by 1/2 or divide by 2. So that's the mean. And when we've done that, and I print it back out again, all of a sudden, oh, I didn't run that. Print it out again, and our temperature, we now think for the 14th of November, we didn't have any data before, now we think it's 6.05 degrees. Okay, I don't really care that that's the 2 decimal places now, not bother. Now we've got this other one. Now, for this one, the last one we just cleaned, the 14th of November, we looked at what happened on either side and took the average. You can take the average of more data and end up with a smoother thing. You could be harsher. There's a whole host of different ways. I've got someone just about to start doing a PhD with me on data imputation models and methods and ways of filling in the blanks. So let's go back to this other one then. you could fill it in again using a statistical approach, but just use the data beforehand and take the middle value, the average or the median. So I'm going to take the data from row 355 all the way up until 361. That was our last good data point. So for this one, minus 72 here, I'm going to ignore the one that I've just filled in. I'm going to use the last good data point I had. So from the 13th, and I'm going to take a week's worth of data. So from row 355 to 361, get the middle value, the median, and then fill that in. So now when I print it, it reckons that that temperature was 9, 6, 9, and then 2. Okay, maybe it hasn't captured a true downward trend that was happening, or maybe it was going to be a nice warm day that day anyway before it had a cold snap. Okay, so we've filled in our data. Let's have a look at what it looks like now. Yep, Shemai. So through the whole, so what we had, let me just go back and look at it. We had 3 missing pieces of data: 4th of January, 14th November, 15th November. Okay. For the 4th of January one, we just dropped it from the data set. We said, you know what, don't care about that one, get rid of it. And we could have done that for all 3, but if you've got lots of missing data or need to get as much data as possible and use as much as possible, you don't want to be dropping it from your data set. So I just dropped it, the 4th of January one. Second one, I said, look, 14th of November is missing. I'm going to say 14th November is the average or the mean of the temperatures on the 13th and the 16th of November. So just add it together, 13th and the 16th, divide by 2, that's the mean. So that filled in a temperature of 6.05 degrees. I then said, what you also could do, instead of just looking before and after and taking the average of 2, you could look over the last week, take the median temperature or the average temperature of the last week and say it's going to be that again. So the weather this week is about the same as last week.
So did you like just take a different approach for both of the, oh, so it wasn't like you just chose to show us 2 different approaches that you could get the data? Okay, yeah. Brilliant. All right, thank you.
Yeah, two different approaches. They're based on the amount of data that you have, reliability, or your own preferences, but it's just, here's 2 different ways of doing it.
All right, brilliant, thank you.
Not necessarily the one's better than the other or anything. So this is what our data looks like now. We now have no missing data. When we plot it, and I'll just rerun this, we'll plot again, and that's our data for 2018. Great. If the data is missing, say, for more than 10 rows, then do we have to work on each row individually, or is the way to do it together? For the purposes of today and for the start of your course, you do it individually. Okay, better to do that. That gets complex if you've got lots of rows missing in a run. Okay, and that's where you need to understand more of the data and more tools and techniques. So we now have a nice plot for 2018 for Vienna. That we filled in the data. Doesn't look a mess anymore. You can't really tell actually where November would have been about here, but it doesn't look like there's an isolated point that we filled in that's wrong or anything. It looks okay. We can also do clever things, so we can get the maximum value for 2018 and the minimum value. So the maximum value was 27, the minimum value was minus 10. The reason I'm showing you these 2 is this may be something you want to look into for different cities once you've cleaned the data. And look at trends of maximum values over time. So go away, look at a city over years, and look at other cities around that. Get the maximum values, append those to a list each time. So go back to the first session I did and create a list and append the maximum value each time, or record them however you want to. That's fine as well. I don't care if you just do the maximum value, rerun the analysis for 2018, 17, 16, 15, pen and paper, write it down, and then write them all in and plot them on a graph. Great. And put a nice trend line in and say, we can see that the trend's increasing here, but the minimum data is, the minimum temperatures are all over the place. Maybe that's an interesting thing. But I just wanted to show you that's how you get the maximum and the minimum values. Okay. So that's the end of my analysis for the temperatures data set for Vienna. What I'd like you to do as a group is to go away, take this data set, take this notebook which it was in the download, the files download that Alice shared. So have a quick download of that. Get it up, rerun this stuff for Vienna individually, make sure you're comfortable with that. And then give yourself a lunch break, probably meet back at about 1 o'clock to start with, and think about the kind of questions that you want to ask of this, the kind of cities or regions or things that you want to look at, and try and find and explore the data and find something interesting in that. And it might be interesting because it completely confirms your own assumptions or knowledge, or maybe it really challenges something and the data's got something weird to say, but you'll only find that when you explore it. So as a group, decide on some hypothesis or thing that you want to test, and then go away and try and do that. Whether you want to have one notebook that you all work on together that you share, or a notebook that you each work on and say, I'm going to work on this city, you work on that city, or us three will work on this, you three work on that, and then do it, and then get talking. But you've each got a Teams call so that you can have audio and you can chat through the thing, you can share your updates and things. So I would like you to create a PowerPoint presentation. So a PowerPoint presentation that tells some sort of story and shares what you found when you've explored. In that presentation, I'd like you to use no more than 5 PowerPoint slides, 5 slides total, to show the plots or the data or to tell some of your story. Okay, you don't have to narrate it or anything. Those slides in and of themselves, I'll be able to understand, I think, from the slides exactly what analysis you've done, so it should be quite clear based on the trends and the data and things. Okay. So make sure that you go and try and do that, but do something interesting, something that you're interested in. Choose some cities and temperatures that you want or trends that you want to look at. Make sure that you clean the data. That's why I've shown you about this data cleaning pipeline there. You can go and find the rows and don't just use the same rows that I've used, because they'll be wrong for different cities, different years, different periods. Okay, but use this code if you want to, and adapt it to try and suit. So the submission point for everyone is going to be 11 AM on Friday morning. Okay. 11 AM UK time. Once you've all submitted that, we're going to come back together in the main call, and I'm going to be talking about AI ethics from the IBM Open Data Science for All course. We've got a panel that's going to be looking at each of the submissions, ranking them, and then, as I'd said on Monday, the team that's come up with the absolute best data exploration system. I'll reiterate that in a second also. The team that's come up with the best submission will be put forward for an internship for a data science project, ideally starting in the first semester, at the end of the first semester, to get some hands-on experience in data science. Okay, so thanks, Yasmin. So Friday UK time, 11 AM. Submit a PowerPoint presentation or whatever slides presentation, PDF or whatever, I don't care format, but 5 slides maximum, and make sure that they tell some sort of story and have done some data exploration. Okay, you've all got the Teams links. Work as your teams, decide on jobs, roles, who's going to start to create the presentation, who's going to analyze which cities, which regions, which things you want to find out. Okay, if you want to look at really far in the past or really recent, think of any limitations as well that show an understanding of what you've done over the last couple of days in terms of the data science courses that we've done and the things that we've discussed. Does anyone have any questions? Okay, now one thing that we've done, I could not find the link for the group 10 in the email. So that's quite strange. Has anyone in group 10, in fact, Yasmin, if you could just quickly grab the email that's got the invite and then share the link with Walija, please. Now, you should be able to enter those teams yourselves. So for this, there has been a lobby that people have had to get accepted into over the last couple of days. I've tried to set the permission so that you can just enter straight into your group one. So if I could just ask someone, Alice, if you don't mind just jumping, given that you've been very on the ball, can you just try jump into your team call the group 9, and then come back in here just to confirm that you can actually get straight in and don't have to wait in a lobby. Thank you. So for everyone else, if you haven't been allocated a team or got a team link, let me know and I'll share with you a team link and allocate you to one. But otherwise, you should all have everything you need to get going. Now, obviously, it's going to be a challenge to do some of this.
Yeah, no problem, straight in.
Perfect, thanks, Alice. So it should be the same for everyone else. I've set the same permissions for all, but if you've got an error, let me know. So Abdul, in the Colab notebook, remember what I did? Before I even started doing this CSV data, this city temperatures data, I went here, clicked on this box, and then said run time, run everything before. Okay, it hit an error because I haven't put up the Hubble data, but that was from day one. But what the line above the Hubble data thing is that it imports or brings in pandas, loads it into the system. Therefore, you can use it. If you don't do that, then you try and do this and it goes, I don't know what this pandas thing is. Python starts off fairly stupid. Okay, so that's the crux of it, really. You have to do everything beforehand and then go to it. So then you can play and off it goes. It should all work then. Okay, now we've got support over the next couple of days. So from about 1 o'clock onwards, we're going to be taking a lunch break next, but from 1 o'clock onwards, Mohammed and Yasmin, both of which have done the MSc AI, are doing their individual projects right now and have done great, absolutely brilliantly on the course. So you're really fortunate to have such proactive learners there. So they're going to be supporting you and just dropping into your Teams calls periodically, one by one each, and they're going to be checking if you've got any questions, just either about this problem, any of the coding stuff. If you're stuck, they might not be able to answer the question straight away because I haven't really given them much notice based on this data set and this problem, because it's of the speed with which we've had to create this and set this all up to make sure it's suited over the last couple of days based on everyone's experiences. But they're good with programming, so even if they don't have an answer for you straight away where you say, this data describe isn't working for me, they'll be able to go away, search it, and then come back and say, look, it's not working possibly because of X, Y, and Z. I found it by typing this into Google, came up with this explanation, have a read of it, but also here's what you need to do. Okay. And it would be the same for me. If you said, if I jumped into your call and you said, Ian, this code isn't working, I might go, well, I don't even know what it does yet. Give me a second, let me read it, understand it, might need to search away, and then go away and explain. Okay, and fix it for you. So they'll be able to do that and to talk you through some of the data stuff, maybe give you some suggestions if you want to talk through your data exploration aspects or things that you're planning on doing as a group. Then they may be able to give you some pointers or suggestions to try and push that further, or things you might want to find out or think about when you're doing that. Okay, bounce ideas off them. If there's any serious issues or questions as well, I will be available over the next couple of days periodically to drop into stuff, but less available than Yasmin and Mohammed. They're going to be your go-to. Okay. They do have access to all of the calls, so they'll be dropping in, but they're not like dropping in to observe you or anything. They're not feeding anything personally about contributions or all that stuff back to me. Like I said, some of you groups are going to have more people available to work, and some are going to have less because of work time constraints and things. We're going to be conscious of that in our feedback and in our rankings of things, but ultimately we'll be able to explain which group we think has performed the best at the end. But the thing that you're getting from this most of all is some experience and some comfort with programming and with us as a teaching team and as a support team before September. So that's the real gain from this hackathon. Okay, so Friday, 11 AM, 5 slides maximum. Okay. Also, feel free to ask Yasmin and Mohammed any questions about the MSc AI from their point of view, any recommendations they have. Okay. Now, I've just remembered one final thing before we close this off. There was a question I received, a great email from someone about could we get an AI system to almost make me obsolete in terms of the recruitment process? When people are applying for the course, could an AI read CVs, personal statements, and decide whether or not to offer a place? Yes, it would be possible in theory, and we talked about this a little bit yesterday, but it gets it's quite hard because we don't have a lot of past data for the course to show an AI algorithm to say this is the way that you should be doing it, and how you should be making classifications and things. But also I don't have an overly great trust in that identifying the most motivated people. I said this at the end of the session yesterday. You're all here and coming, going to be getting onto the course if you're getting on because of your motivation, your keenness, because of the drive that you've got and the way that I believe in you and think that you're going to succeed on the course. Not necessarily because you've got a first or you've done a PhD in X, Y, and Z. That stuff, maybe it'll help you, but it doesn't necessarily help me understand whether or not you're going to be motivated and you're going to succeed. This is a hard course, but it's going to be really rewarding. We're going to do our best to support you, but naturally there's a lot to learn in a year. And I think Yasmin and Mahal would completely back me up in that. So motivation is the most important thing. And even I've had a few years of experience trying to identify and work with admissions and students and profiles and things. And even still, I'm amazed at how on paper, people who look very strong applying for the course, and people who look slightly weaker on paper in terms of academic profiles and their motivation is good but not necessarily the best at the application stage, how well they can perform. And in terms of the group profile, I'd have been quite wrong if I'd put money on where I thought people would have ended up in terms of the grade profile for this course. So it's really exciting for me as an academic to teach that. But ultimately, no, an AI algorithm wouldn't necessarily be overly reliable replacing me. Not yet, anyway. Okay. Does anyone have any other questions that you want to bring in before we close this off? Take a lunch break and then you get started on the hack? All good to go. Excellent. That's great. So the recording for this session, I'm just about to stop it now. That will be going online as quick as I can get it online in case you need to watch back any of the aspects that we just covered and my explanations of that code for the data cleaning bit. So I'll email you all when that's available. Okay. But other than that, good luck working your groups. Have some fun. Try not to stress about it too much and just enjoy and try different things. Use Yasmin and Mohammed because that's what they're here for, to help support and to push you and help you do better and to learn more. Great, thanks Alice. And I look forward to seeing you on Friday at 11 AM so we can talk about AI ethics as a good way to round off this week, and then the prize will be nominated. Thanks very much, everyone. If you've got any questions, again, feel free to ping me a message to my inbox using that question in the subject line. But otherwise, enjoy and see you on Friday.